Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay. So this is the lecture number 10 in which I'm going to discuss second order phase transition, Joule-Thomson effect, and also the Maxwell-Boltzmann distribution. Okay, so guys, also I would request the students who haven't subscribed my channel yet, please guys subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay, and also guys, please share my lecture details to your friends so that they will also uh, get the opportunity to watch my free live lectures and will be benefited from it. Okay, so let's get started guys. Okay, meanwhile just let me check whether I'm audible or not, then I'll proceed further. To watch my free, yes, I'm audible, so I'll proceed further. Okay. Okay guys, so second order phase transition. Okay, second order second order phase transition. Second order phase transition. Okay, second order phase transition. Second order phase transition. So in second order phase transition, no heat energy is absorbed or liberated. So we have seen in first order transition, which I have already explained in my previous lecture, that there is heat energy absorption and that liberation, right? But in second order phase transition, there is no heat energy absorb not heat energy absorbed, not no heat energy absorbed or liberated. In first phase or in first phase transition, there is heat energy absorbed or liberated, but in this in second order phase transition, no heat energy absorbed or liberated. Okay, second point is no latent heat required. Okay, no latent heat required. Okay, so in second order phase transition there is no latent heat required. Okay, but we have seen in first order transition there is latent heat involved in the first order phase transition, but in second order phase transition no latent heat required. Okay, next is smooth transition. Okay, smooth transition. Transition is smooth. Okay, smooth transition. And next point is no time gap. Okay, so there is no time gap. No time gap. In transition, there is no time gap. Okay. So example of second order phase transitions are, this is for example, that is normal conductor, normal conductor becomes superconductor. So normal conductor becomes superconductor, or superconductor becomes normal conductor, right? So this is the second order. So the transition of normal conductor to superconductor and superconductor to normal conductor is example of second order phase transition, right? In first order phase transition, we have seen ice melts, becomes water, and water to ice, and similarly water to vapor, vapor to water, right? So this is the first example. Second example is paramagnetic substance. Right? Paramagnetic, paramagnetic to ferromagnetic, and ferromagnetic to paramagnetic. Okay, ferromagnetic. So transition from paramagnetic to ferromagnetic and ferromagnetic to paramagnetic. This is also example of second order phase transition. And next example is this one. Liquid helium first becomes liquid helium second. Helium second. Liquid helium first becomes liquid helium second, and liquid helium second becomes liquid helium first. Okay, this one. Okay, next is G is continuous in the first order. In the second order phase transition, G, that is Gibbs free energy, is continuous. In first order phase transition also the Gibbs free energy is continuous, guys. We have seen. Okay, this is Gibbs free energy. Gibbs free energy. Okay, in second order transition, S is continuous, entropy is continuous, and also V is continuous. V is continuous. So we have seen S is derivative, or S is equal to derivative of Gibbs free energy, and V is also derivative of Gibbs free energy. So this means in it means in second order phase transition, the derivative of these are continuous, right? So derivative of first order derivative, first order derivatives of G, is also continuous. We have seen in first order phase transition, the first order derivatives of G are discontinuous, right? So here the first order derivatives of G, that is S and V, are continuous. Okay. Next point. Second order derivatives of G is discontinuous. Okay. So second order derivative, second order derivative of G is discontinuous. Okay. Second order derivative of G is discontinuous. In first order phase transition also second order derivative of G is discontinuous, right? Next point is the heat, specific heat. Okay, specific heat. So in case of first order phase transition, we have seen that it has infinite discontinuity, right? In first order phase transition, specific heat has infinite discontinuity, and in case of second order phase transition, it has finite discontinuity. Okay, finite discontinuity. Okay, so specific heat has a finite discontinuity. Okay, in case of second order phase transition. Okay, I'm comparing both first and second so that it will be easy for you to understand. Okay, and if you talk about first order phase transition, specific heat has a infinite discontinuity, which I have already explained, guys, in my previous lecture. Okay, next is susceptibility. 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 Okay, susceptibility is in second order phase transition, that is discontinuous. Okay, so susceptibility is discontinuous. Susceptibility is discontinuous. Okay. Next, I'll compare this liquid helium first and second. Okay, what is the difference between them? Liquid helium first and liquid helium second. Okay, liquid helium first and liquid helium second. Liquid helium first and liquid helium second. So first, if we talk about density of liquid heliums, okay, so that is in first order in liquid helium first, if T increases, so my apologies, if T decreases, implies the density of this row, density of liquid helium first, also decrease, but the density of liquid helium first is increases. Okay, in case of this one, the liquid helium second, if T decreases, temperature decreases, in that case P increases and goes to max value, and then it decreases. Okay, so this is the difference. If we talk about density, if we decrease the temperature of then density increases in case of liquid helium first, and in case of liquid helium second, if T decreases, P increases and goes to maximum value, and after that it starts decreasing. Second point is, if we talk about specific heat, that is C. So here T decreases, if T decreases, that implies in liquid helium temperature decreases, then specific heat increases. Okay, if you talk about liquid helium second, if we decrease the T, then what happen is C increases, okay, at 2.19 Kelvin till 2 point and at so C increases, and at 2.19 Kelvin, at 2.19 Kelvin, uh, it gets maximum value. Okay, and then it starts decreasing, and then the C starts decreasing. Okay, okay, and next point, if we talk about viscosity, so if T decreases, that implies viscosity that is increases, guys, in this case, simple. But if we talk about liquid helium, so T decreases, that implies viscosity increases. Okay, viscosity increases, okay, and then decreases, then decreases. Okay, after getting the maximum value. Okay, so this is the difference between liquid helium first and liquid helium second. Next, I'm going to make a graph between this Gibbs free energy, okay, versus temperature, right? This is G versus temperature, and next graph is this one, T versus S, entropy. Okay, next one is T versus this V, volume. Okay, and then T versus Cp. Okay, that is specific. Okay, so here you can see, So if you talk about G, okay, the graph is continuous. Okay, so if you talk about this, I have already explained, right? So that entropy, that is the first derivative of G, that is also continuous, right? So volume, that is also first derivative of G gives free energy, that is also continuous. If you talk about the CP, that is specific heat. So specific heat had I told you it has finite discontinuity for second order phase transition, means the graph is like this. Okay, so it has finite discontinuity. So these are the graph, guys. Finite discontinuity, these are continuous. Okay, finite discontinuity. Okay, finite discontinuity. Next. Next is Joule-Thomson effect, guys. Okay, Joule-Thomson effect. Joule-Thomson effect. Okay, so very important topic and very simple. So guys, so this is, we have an isolated system. Okay, so there is no transfer of heat between system and surrounding. Okay, so there is a wall and there is a high pressure liquid. It's a liquid whose pressure is very high. Okay, high pressure liquid P1 liquid, and there is low pressure liquid whose the pressure is P2. Okay, and volume of this is V1, volume of this part is P2. Okay, and P1 is greater equal to P2. P1 is greater equal to P2. Pressure P1 is high. So if you remove this wall, the liquid starts flowing from high pressure to low pressure, right? So in that case, because there is no that it's isolated system, right? Isolated system means del Q is going to be 0 because it's isolated system. Isolated system. Del Q equal to 0, it means from first law of thermodynamics, du plus del W are going to be 0 because del Q equal to 0, right? So from here, du plus del W is going to be 0, or we can write du means this one, u2 minus u1, right? u2 minus u1 plus dw is pdv, right? Pdv means this one, or we can write like this, pdv. Right? So this is going to be u1 plus u1 minus u2, and here it is going to be p2 v2 minus p1 v1, p1 p2 v2 minus p1 v1, right? So from here, u2 plus p2 v2, that is going to be u1 plus p1 v1, and this means u plus pv equal to constant, and u plus pv we know that is h enthalpy, so uh equal to u plus pv, that is constant, okay? So this is h is enthalpy, guys, very important. H is enthalpy, so this is enthalpy, okay? And here that this implies this is constant means dh, that is change in enthalpy, is going to be 0. So that means this is iso enthalpic process, right? Isoenthalpic isoenthalpic process. isoenthalpic process. Okay, so this is a isoenthalpic process because here H is constant and that is del H is value of del H is dH is 0. Okay, next is so from here you can write since del T upon del P at constant temperature, a constant enthalpy at constant enthalpy, that is going to be that is going to be value is 1 upon CV TdV upon delta TdV upon delta T, right, and minus V, and that value is mu H. Okay, so dt upon dP at constant H is equal to 1 upon CV TdV dt minus V equal to mu H, and mu H is called Joule-Thomson coefficient. This is important one. Okay, so this is Joule-Thomson 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 coefficient. So this is Joule-Thomson coefficient. Okay, well, and this is important result, guys. You need to note down. Okay, so the del T upon del P at constant H equal to 1 upon CV T dV dt minus P equal to mu H, and mu H is Joule-Thomson coefficient. Okay, well, this is the one. Or we can write this one del P over del P at constant H equal to, this is guys this at constant P, right? Okay. 1 upon Cp T into del V over del P at constant P. Okay, this is Cp. Constant P minus P equal to mu H. Okay, this one. So for if we talk about for an ideal gas, okay, for an for an ideal gas, for an ideal gas, we know PV equal to RT for 1 mole of gas, right? So from here V value is going to be RT upon P, RT upon P, that implies mu H value is going to be 1 upon Cp, 1 upon Cp T into RT minus T into RP, okay, because here PV equal to RT, right? So P value is this, so this is the V value, right? Del V upon del V, we are differentiating with respect to this one T, right? So this is going to be del T upon del P. This is del V upon del P, right? This one. So del V upon del T equal to, if we differentiate this, this is del V upon del P. That means del V upon del T at constant P. That is going to be R of P. Right? We have put this value del V upon del P here. This value. So this if you solve it, this value is going to be 1 upon Cp into Tr, because Pv equal to RT means Tr equal to Pv. Pv will get cancelled, right? That is V minus P. That is going to be 0. Okay, since Pv equal to RT or Tr. So instead of Tr, we have to put Pv. Pp will get cancelled, V minus P equal to 0. So mu H equal to 0. For an ideal gas, the Joule-Thomson coefficient is 0. Okay, important one. Okay, guys. Next is for real gas, guys. Okay, for real gas, the mu s value is going to be this one upon Cp, 1 upon Cp, and this value is going to be 2a upon RT. This is for real gas, 2a upon RT minus B. Okay, or we can write mu h, that is equal to, you need to note down, guys, important one. Okay, or mu h is going to be B upon Cp T into 2a upon RB, 2a upon RB minus 1, 2a upon RB minus T, that is T. This is also important one. So here, or we can write mu h equal to B upon Cpt into Ti minus T, where Ti is inversion temperature, guys. Okay, where Ti is inversion temperature. Ti is inversion temperature. Okay, and that value is equal to, Ti value is this one, 2a upon RB. Okay, this one, 2a upon RB. So 1 upon Cpt. So this B. So mu h equal to this is very important. Mu h equal to B upon Cpt into Ti minus T. Okay, where Ti is inversion temperature. Okay, where Ti is inversion temperature. Okay, and this and Ti value is this 2a upon RB. 2a upon RB. Important one. Okay, so there are 3 different cases. So if Ti is greater equal to T, okay, if Ti is greater equal to T means this mu h value is going to be positive. That means mu h value is positive. So that implies this is cooling, right? Okay, so means there is a cooling in the system, cooling. And second case is if T inversion temperature is uh, less equal to T, less equal to T, less equal to T, less equal to T means this if Ti is less equal to T means this value is going to be negative, right? So that implies mu s, that Joule-Thomson coefficient value is going to be negative. Negative, it means heating. Okay, heating. And third is if Ti that is equal to T, both temperature are equal, Ti and T, inversion temperature and temperature. In that case, mu h value is 0. It means mu h is 0, and that means neither heating nor cooling. Okay, neither heating nor cooling. Neither heating or cooling. Okay, neither heating nor cooling. There is no heating, no cooling. Okay, neither heating nor cooling. Neither heating nor cooling. Okay, this is the one. Okay. Okay, guys. Now Maxwell-Boltzmann distribution, guys. Okay. Maxwell Boltzmann distribution. Okay, so this is Maxwell Boltzmann distribution. So guys, here we know that Fv is equal to a into e to the power minus beta e. Okay, this is the function. Okay, Fv equal to a into e to the power minus beta e, where e for classical particle, Max Boltzmann distribution is for classical particle, and for classical particle E is going to be half mv square, since potential energy for classical particle is 0, right? And beta value we know that is 1 upon kT. Okay, so in that case Fv, that distribution function is going to be a e to the power minus mv square upon 2k, right? Because beta e value is half mv square, and beta value is 1 upon kT. So a e to the power minus mv square upon 2. Okay, so from here that fv, that function is going to be fv dv. Okay, fv dv is going to be, that is 4 pi n, important one. Okay, 4 pi n m upon 2 pi kt, m upon 2 pi kt to the power 3 by 2, and then v square e to the power minus mv square upon 2 kt dv. Okay, so this is the Maxwell distribution function. Okay, this one. Okay guys, important, this one. Okay, well, so this is the Maxwell Boltzmann function. Okay, now I'll discuss this value, fv value, 2d, 3d, and 1d, right? So in 1d, this distribution function is going to be fv dv. In 1d I'm talking about. Okay? Fv dv is going to be n into m upon 2 pi kt to the power half, and this is going to be e to the power minus mv square upon 2k. Okay, so dv. So this is the Maxwell distribution in 1d. In 2d, it is going to be fv dv. That value is going to be 2 pi n m upon 2 pi kt to the power 1. Okay, there is no power, and v e to the power minus mv square upon 2 kt dv. Okay, and in 3d it is going to be fv dv. That value is going to be 4 pi n m upon 2 pi kt, m upon 2 pi kt to the power 3 by 2 v square. Okay, e to the power minus m v square upon 2 kt. Okay, so this is in 3d, which is the same, right? So in 3d it is fv dv, that Maxwell Boltzmann distribution function, is 4 pi n m upon 2 pi kt to the power 3 by 2 v square e to the power minus m v square upon kt, right? For 2d this power will be 1, or for 1d power will be 1 by 2, right? 3 by 2, then 1, then 1 by 2, or 1 by 2, then 1 by 2, 1, and 3 by 2. Okay, in this fashion. So this is the distribution function, and I'll make a formula. So here, if we draw the graph like this one, this is v versus fv. Okay, then this is this graph is going to be like this one. Okay, so here this value is vmp, that is most probable velocity. Okay, and then this value is going to be, this is V average, this is V average value, okay, and here this value is VRMS value, VRMS. Okay, so this is the graph versus that V versus FV, function of V, okay, and this is the highest value corresponding to, this is most probable velocity, this is average velocity, and this is VRMS velocity, okay, and this is like e to the power minus mv square upon 2 kt, okay, and this is that alpha v square proportional to v square, right? So this is the graph, guys. This one. These velocities are important: VRMS, V average, and VMP. Okay, most probable velocity. Okay. Okay, guys. Next is most. Now I'll explain most probable velocity. The most probable velocity. That is most probable speed, guys. Most probable speed. Okay, and that is most probable speed. What we do is dfv upon dv. That is should be 0, right? So that implies vmp, most probable speed v is going to be, that is most probable speed is going to be 2 kt upon m, or we can write 2 rt upon m. Okay, since we know r equal to na k is the Boltzmann constant, n is the Avogadro number, and m value we know, m value is m into na. Okay, so so from there the most probable speed is root 2 kt upon m or 2 rt upon m. Okay, so this is the one, guys. And similarly, average speed average speed average speed equal to root v fv, that function of v, that is function of v, upon root fv dv, right? This is going to be that average velocity, that is, guys, 8 kt upon pi m, or we can write 8 rt upon pi m, 8 kt upon pi m or 8 rt upon pi m. Okay, this is the velocity, the average velocity. And then rms velocity, rms speed, it's speed, guys. Okay, rms speed, that is v square, average of v square root, right? This is rms root mean square velocity, right? And that value is this one, root v square fv dv upon fv dv. Okay, v square fv dv upon fv dv, right? And that value is going to be root 3 rt upon m, root 3 rt upon m, or root 3 kt upon root 3 kt upon m. Okay, this one. And the average speed is root 8 kT upon pi m, root 8 kT upon pi m. This is 3 kT upon m, and most probable speed is, this is 2 RT upon m or 2 kT upon m. Okay, these are important things. Now I'll make a graph. These values, this most probable velocity, RMS velocity, and average velocity in 1D, 2D, and 3D, right? So I'm going to make a table. So this is most probable velocity, and this is VRMS, and this is V average. Okay, this one. Okay, so in 1D, this value VMP value is 0, and this value is root KT upon M. Okay, and V average. So VMP, then V RMS, and then V average. Okay, and this is going to be root 2 KT upon M. This is in 3D. If we talk about 2D, so that is going to be KT upon M, KT upon M, root KT upon M. This is this is root KT upon M, 2 KT upon M, and in 3D this is going to be pi KT upon 2M. Okay, and in 3D, if we talk about, in 3D, this value is going to be this value is going to be 2 KT upon M. Okay, this is 3 KT, root 3 KT upon M, and this is 8 KT upon M, 8 KT upon pi M. So simple way to remember this is, in 1D you will start with 0, then KT upon M, then 2 KT upon M, 0 KT upon M, 2 KT upon M. Okay, in 2D KT you will start with KT upon M, KT upon M, 2 KT upon M. This value is different, this you need to note down. This is pi KT upon 2M. Okay, pi KT upon 2M. In third you will start with 2 KT upon M, 2 KT upon M, 3 KT upon M. This value is different, guys. This is 8 KT upon pi M. 8 kT upon pi m, and this is pi kT upon 2. Okay, in this way you can note down. So these are the different velocity: most probable velocity, VRMS velocity, and average velocity. Okay, so so you need to write in this order: most probable velocity, then VRMS, and then average velocity. Okay, well guys, so I'm going to stop here, and also guys, I would request the student who haven't subscribed my channel yet, please subscribe my channel guys, and watch my free live lectures which are going to help you to crack the exams related to physical science. And also guys, please share my details with your friends so that they will also be able to watch my free live lectures and will be benefited from it. Okay guys, thank you so much. Bye now.